So in this video we are going to discuss the questions that appeared in physical science examination June 2018. The first question is, which of the following statement concerning the coefficient of volume expansion alpha and the isothermal compressibility kappa of a solid is true? So the options are, if alpha and kappa are both intensive variables, and alpha is an intensive and kappa is an extensive variable, alpha is extensive and kappa is an intensive variable, and the fourth one is alpha and kappa both are extensive variables. So before we take a decision here, let's try to understand the basic definition of these two quantities. The first one is alpha, which is the isobaric expansivity, and it is defined as fractional change in volume, that is delta V by V. That's a fractional change in volume, because this is the expansivity, it's isobaric expansivity. So if you just take a general idea from our daily life, expansion it is with respect to temperature, so it's fractional change in volume with respect to temperature, okay, and the constant is a constant pressure here, okay. And the second quantity is the kappa T, okay. This is the isothermal compressibility, so its definition is minus 1 by V. That's a fractional change in volume, and because this is the compression, so compression is with respect to pressure here, and it is taking place isothermally, okay. Now here the negative sign is because when we increase the pressure here, so for increase in pressure, correspondingly there will be a reduction in the volume, okay. So that's why to make this quantity a positive one, this negative sign is introduced intentionally. Now these two quantities, these are basically, they do not change. These are the intensive variables, okay, intensive variable. So that is, these are intrinsic parameters, okay. These are exactly similar to the what you call them as the specific heat capacity, Cp and Cv. Note that these are not the principal heat capacity, these are the specific heat capacity at constant pressure and constant volume. So therefore the correct option is alpha and kappa T. These both of these two quantities, they are intensive variables. So let's continue with the next question. The question is, the number of ways of distributing 11 indistinguishable bosons in 3 different energy level is, okay. So what we are given is, we are given n is equal to 11, and these particles are indistinguishable, okay. And in principle these are bosons, okay. And here what is G? The number of cells are G, that is equal to 3. So if you just recall the theory that you might have learned in elementary classes, the number of different ways, the number of ways of distributing n boson in G cell, that is given by the expression omega VE, that is equal to n plus G minus 1 factorial divided by n factorial multiplied by Gi minus 1 factorial. So here we are given these two quantities, and this is equal to 11, n is equal to 11 here, and G is equal to 3. So 11 plus 3 minus 1, its factorial, divided by 11 factorial, and then 3 minus 1 factorial, okay. And this turns out to equal to 11 plus 3 14 minus 1 13 factorial divided by 11 factorial and 2 factorial. So I think C is the correct option here. So therefore C is our answer. So let's continue with the next question. The statement is, in a system of n distinguishable particles, here we are given n distinguishable objects basically, okay, each of which can be in two energy states. Okay, let's draw the energy levels which are with value minus E and 0, and since nothing is mentioned about the degeneracy, so we can take G to be equal to unity for both of these two energy levels. Okay, the mean energy of the system at a temperature T is, so we have to identify the correct options. Okay, let me here actually there is a mistake here. It should be divided by here minus Ne divided by this expression, and here also it should be plus Ne upon, okay, it should be plus Ne and divided by this. This is the correct option which were given in the paper basically. Okay, so there is a typing mistake here. Okay, so let's try to find out the average energy for the system of n distinguishable objects. Okay, and we can do this by adopting the partition function approach. So partition function for single object Q1 TV, that is equal to summation Gi exponential minus beta Ei and over I. Okay, so because G it's given to be unity here, okay, so this can be rewritten as, for the corresponding energy levels, G1 exponential minus beta E1 plus G2 exponential minus beta E2, and if you just substitute the value G1 and G2, they are 1, so this comes out to be equal to exponential beta E plus G2 is 1, so plus exponential minus beta multiplied by 0, so that will give you 1. So this is the partition function for single particle. Okay, now the mean energy per particle, that is average of E, note that this is per particle, and this is equal to minus curly beta of ln Q1 TV. Okay, and this is equal to minus curly beta of ln 1 plus e power beta E, and this is further equal to minus 1 upon 1 plus exponential beta E exponential beta E and then multiply by E, its differential with respect to beta, and this is equal to minus E power beta E upon 1 plus exponential beta E, and in principle this can be rewritten as, this is minus E divided by 1 plus exponential minus beta E. So basically we are bringing this exponential factor into the denominator. Okay, now this is the average energy per particle. So therefore for the n particle system, the average energy will be simply U, because it's a system of distinguishable objects, and that's simply the n multiplied by the average energy per particle. So that is equal to minus Ne divided by 1 plus exponential minus beta multiply by E. So this matches with the option D here. Okay, so therefore D is the correct option here. Let's take a look at the next problem. So we are given the van der Waals equation of state for 1 mole of a gas. Okay, the corresponding equation of state for n mole of this gas at a pressure P, volume V, and temperature T is given by. Okay, so we can quickly obtain these results by simply making use of the van der Waals equation of state for 1 mole of a gas, and that is given by in principle it's given to us. Okay, so P plus A by B square into B minus B, that is equal to RT, and this is valid for n is equal to 1 mole. Okay, now this equation can be transformed for a system having n moles by simply replacing volume as volume per mole. Okay, if you do that, So then we can rewrite this equation as P plus A Vy n square multiply by Vyn minus V, and that is equal to RT. Okay, and after solving this, P plus A n square upon B square, and then B minus NV by N, that is equal to RT, and after final rearrangements, this comes out to equal to P plus A n square by B square multiply by B minus NV, and that is equal to nRT. Okay, so if you just compare the result that we have obtained, so it matches with option A, P plus A n square by V square into B minus NB, that is equal to nRT. So this is wrong. Okay, here it's strange that they have given the two identical options. So in principle this is also true, because it's the same. A and C, they are exactly identical. Okay, D, it's not true. So therefore A and C, these are the correct options here. So let's continue with the next question. The statement is, the pressure P of a system of n particles contained in a volume V at temperature T is given by this expression, where n is the number density. That is, it's given that n, this is the number density, and A and V are the temperature independent constants. If system exhibit a gas liquid transition, okay, the critical temperature is, okay, so we have to find the critical temperature for the system. Okay, so if you just recalled what you might have learned in your the classes, so the critical parameters can be obtained by simply taking the first and second derivative of this equation, the given equation, that's equation of state, you can also call this, and then equating those derivatives equal to 0. So that's the approach we are going to adopt here, and let's try to see what we obtain. Okay, so we are given that, let me divide. So we are given the equation of state like P, that is equal to n kVt. So I will write K simply for the Boltzmann constant here. P, that's n kT minus 1 by 2 A n square plus 1 by 6 B n cube. Okay, where n is the number density, it's given to us. Okay, now so let's call this as equation 1. Okay, now this can be rewritten as P, that is equal to n by B kT minus A by 2 n by V its square plus B by 6 n by V its cube. Okay, so we will call this as equation 2. Now the critical parameter can be obtained by simply equating dP by dV at constant temperature, this is equal to 0, and because these are basically differentials, that first order and second order differential of P respect to V and d2 by dV square at constant temperature, this is equal to 0. So that's what we are going to do here. Okay, so now while coming to this first differential, that is dP by dV at constant T, which is basically that will give us the critical temperature basically. Okay, so now we are going to apply this definition on this equation 2. So if we do that, what let's see what we will obtain. dP by dV at T is equal to Tc, and this will be equal to, so if we take its differential of the first term, so that will be so minus 1 by b square, a factor of minus 1 by b square. So this, the first term will be minus n kT upon b square. Okay, now from the second term we will obtain, if you just keep the constant terms outside, minus a n square by 2 and then 1 by v square, its differential, so that will give us a factor of minus 2 by b cube. Okay, now come to the third term. So this is b n cube by 6, you keep it outside, b n cube divided by 6 and then differential of minus 1 by b cube, so that will give us minus 3 upon v power 4, and this should be equal to 0. So after rearranging these terms, we are going to bring this nkt by v square on the left hand side. So this can be written as n k tc, because this will give us the critical parameter tc, and then we are going to place it with the critical volume v square, and this will be now the remaining terms, these two terms on the right hand sides. Okay, so this is equal to a n square upon vc cube minus b n cube upon 2bc power 4, and let's call this as equation 3. Okay, now we are going to determine the second derivative by making use of this expression. Okay, so we are going to differentiate it with respect to b. Okay, so the second derivative, that is d2 p upon db square at t equal to tc, that is equal to, now dp by dv, so here minus nkt outside and then the differential of 1 by b square, so that will give us minus 2 by b cube, so minus and minus, that will become plus, so I'm writing the result directly here. So 2 nkt, this is equal to 2 nkt upon bc cube. Now the differential of the second term, this one, 2 and 2 will cancel with each other, so this will be a n square multiplied by minus 3 by vc4, so plus a n square multiplied by minus 3 by bc power 4. Okay, now the differential of the third term, so minus b n cube divided by 2 and the differential of the volume term minus 4 by bc power 5, and this should be equal to 0. Okay, now this can be rearranged further as, because we are equating it to be equal to 0, so this can be rewritten as 2 n kt upon bc cube, and this is equal to 3. Now these two terms on the right hand side, 3a n square divided by bc 4, the first term. Okay, now the second term, okay, minus 2b, so 2 will cancel with the 4 here, so we'll left with only a factor of 2 here, so minus 2b n cube minus 2b n cube divided by bc 5. Okay, so here again we will make use of this result, because we are having n kt by bc cube here, so here we will keep aside 2 by bc and then we will substitute the value of this factor here. So this equation can be written as 2 divided by vc then multiply by n kt upon bc square. So that means we did this step intentionally so that we can make use of this result here, and this is equal to 3a n square upon bc4 minus 2b n cube upon bc5. Okay, now let's substitute the value of this quantity here in this equation, so then we will obtain, so let me call this equation as equation number 4. Okay, so 3 and 4 now implies, so 3 and 4 will imply 2 by BC as it is, 2 divided by BC as it is. Now the value of NKT by BC, okay, so that is equal to A n square upon BC cube minus B n cube divided by 2 BC4. Okay, I hope this step is clear, because we have simply substituted the value of NKT by BC square from equation 3. Okay, and this is equal to 3A n square divided by BC4 minus 2B n cube upon BC5. Okay, now we have to simply rearrange the terms, and then after rearranging, what we obtain is, this implies A n square upon BC4, A n square upon BC4 is equal to B n cube divided by BC5. Okay, and after solving, we obtain the critical volume from this result, that is equal to Bn upon A. Okay, we are almost done with this problem, so let me call this result as equation 5. Now put the value of this BC. Okay, so that means put equation 5, that is VC, in equation 3. Okay, let's take a look what is equation 3. So here, so that will put the value of VC here, and then we will obtain the value of the temperature. So let's see what we will obtain. So here, after substituting the value of VC in equation 3, what we obtain is NKTC by BC square basically. So NKTC divided by BC square, which is equal to this expression. So divided by V n upon A, its square, and that is equal to A n square divided by BC cube, so which is B n upon A and its cube minus B n cube divided by 2 times BC4. Okay, so BC is B n upon A, its power 4. Okay, now we have to simply solve this expression. So this implies A square by B square into KT by N, and that is equal to A4 divided by B cube N minus A4 divided by 2B cube N. Okay, and this is further equal to, after rearranging the terms, so this turns out to be equal to 1 by 2 A4 divided by N B cube, and after solving these two expressions, TC comes out to be equal to A square upon 2B KB, where K is the Boltzmann constant. So therefore this is our final result. So let's see which option is the correct one. It's A square by 2BK. It's A square upon 2BK. A square upon 2BKB. So this is the correct option. C is the correct one here. Okay, so therefore C is correct. So let's continue with the next problem. So the statement is, consider a particle diffusing in a liquid contained in a large box. So that means we can treat this problem in 3 dimensions. The diffusion constant of the particle in liquid is given to us. The minimum time after which the root mean square displacement become more than 6 cm is. Okay, so here we are going to start with the certain assumption. So we assume that let nRT be the particle density, nRT be the particle density at position R and time t. Okay, so then we can write nRT, so this is a result that's valid in 3 dimension, and you have to remember this result nRT, that is equal to n divided by 4 pi dt, where d is the diffusion coefficient and t is the time, 4 pi dt power 3 by 2 and then exponential minus r square upon 4 dt. Okay, let's call this as our equation 1. Okay, now the root mean square displacement, that is RMS, that is equal to r square as a function of t and its mean and its root then. Okay, so this is our equation 2. Okay, now by definition this can be written as r square, its average, that is equal to, so we are going to make use of the standard definition of the finding the average. It's from 0 to infinity and then r square and then the distribution function, which is nRT, basically nRT, and the elemental volume d tau. Okay, and then divided by 0 to infinity the distribution function only, nRT. So this is standard procedure for obtaining the average of a physical quantity, and this becomes equal to, now we will substitute the value of nRT and d tau. So d tau in 3 dimensions, it's basically 4 pi r square dr. So that's what we are going to do in the next step. So this is 0 to infinity r square as it is. Okay, and then nRT as it is. Now d tau is 4 pi r square dr and then divided by 0 to infinity nRT 4 pi r square dr. And if we just simply substitute the value of the nRT here and then take its integral, and this will gives us a total number of particles, which is n here. So we need not to worry about the integral in the denominator, so we can directly put this equal to n. Okay, so after the substitution of the nRT in the numerator, so this turns out to be equal to, that is equal to 4 pi this factor and divided by n from the denominator, 4 pi by n, and now what is left in the numerator, it's 0 to infinity, and here we are having r square and this is r square, so this will becomes r power 4 and then value of the nRT. So nRT is, it's this expression 1, so r square multiply by n divided by 4 pi dt, 4 pi dt and its power 3 by 2 and then the exponential factor, exponential minus r square divided by 4 dt and then dr. So some of the terms will cancel with each other, so like n. So ultimately what we are left with is, that is equal to 4 pi this as it is and divided by the other constant term, which is 4 pi d t power 3 by 2, and then inside the integral we are having 0 to infinity r power 4 and exponential minus r square upon 4 dt dr. Okay, so let's call this as equation 3. So here we are going to make use of the one of the standard integral that I'm going to share with you in the next page. Okay, the result that we are going to use is it is 0 to infinity x power 4 exponential minus alpha x square dx, and this is equal to 3 by 8 under root pi by alpha 5. Okay, so the alpha is a constant here, so we will make use of this result in the previous integral, that is in equation 3, and then we will see what we are left with. So r square average, this will be 4 pi upon 4 pi dt its power 3 by 2, and then the value of the integral, which is 3 by 8 under root pi by alpha 5. Okay, so this is under root pi divided by alpha 5. Alpha 5 is 1 by 4 dt, so that means 4 dt power 5. Okay, so after in solving all these values, so at the end we will be left with, so after cancelling some of the terms here, so okay, let me give these details to you. So this is basically, this can be rewritten as, so it will be cancelled with 4, so we will be left with 3 by 2, and then inside the brackets it is pi cube and then 4 dt power 5 divided by 4 pi dt cube and its power 1 by 2, and after solving we will obtain this is equal to 3 by 2 multiplied by 4 dt, so this is nothing but 6 dt. Okay, so now we are almost at the end of the solution of this problem. So what we obtained is r square rms is equal to 6 dt, so therefore r square this is equal to 6 dt. So from here, so this implies t, that is equal to r square rms divided by 6d. Okay, so we are given this r rms, that is given as 6, so therefore 6 square divided by 6 multiplied by the diffusion coefficient that is given to us. Basically we have to find the minimum value of the time t. Okay, so that that will have, occur for the minimum value of this quantity. Okay, so 6d diffusion coefficient, it is given to us 1.0 into 10 power minus 2 centimeter square per second, and after doing the calculation, so this will come out to equal to 6 into 10 power 2 second, so which is nothing but 10 minutes. Okay, so therefore the time is equal to 10 minutes. Okay, so let's see what are the options. Yes, so here therefore the option A is the correct one. Let's take a look at the next problem. A thermally insulated chamber of dimension L, L and 2L is partitioned in the middle. One side of the chamber is filled with n moles of an ideal gas at pressure P and temperature T, while the other side is empty. At T is equal to 0, the partition is removed and gas is allowed to expand freely. So that means a free expansion. The time to reach equilibrium varies as. Okay, so the time to reach the equilibrium, that is time to reach the equilibrium can be correlated with as time, it's the distance which the gas molecule will travel and divided by the average speed basically. Okay, so since we know that the average speed, it is proportional to T by m, it's proportional to the temperature. Okay, and the inversely related to the mass of the gas molecule. Okay, so by making use of this fact here, okay, so we conclude that the time it is proportional to L and T in the under root T in the denominator, so that means T power minus 1 by 2. Okay, so therefore if you just take a look at the options, it is basically okay, it's option C, L T T minus 1 by 2. So therefore C is the correct one. C is correct here. Okay, let's continue with the next question. The statement is the maximum intensity of the solar radiation is at wavelength lambda sun. Okay, so let's write the information that is given to us. So we are given lambda sun, that is equal to 5000 angstrom and corresponds to surface temperature. So corresponding temperature of the sun, it is given to be, that is 10 power 4 Kelvin. Okay, 10 power 4 Kelvin. If the wavelength of the maximum intensity of an X-ray star, so let's write it as lambda star, wavelength of the maximum intensity, it is 5 angstrom. Okay, then its surface temperature, so we have to find the corresponding temperature of the star. Okay, so basically this is a problem which is connected with the Wien's displacement law. Okay, so let me explain it quickly and then we will come to the solution. So as the this is the intensity that's emitted and intensity versus the wavelength as a function of temperature. Okay, so intensity maximum, it occurs at a certain wavelength which we call as the lambda minimum. Okay, so these lambda values for these two different situations, they are given to us. Okay, and we have to okay, so because the emission at this lambda value, this will be different for different temperatures. Okay, so we are having two different situation. Okay, something like this. Okay, so one corresponding to this and another one corresponding to this one. Okay, so this is given to us, let's say this is corresponding to the star and this is 5 angstrom and this value is 5000 angstrom. Okay, so corresponding temperature for this case, it is given to us, it is 10 power 4 Kelvin. Okay, so this is given to us, and corresponding temperature for this case, this is the second case, we have to find it out. Okay, so here we will make use of the Wien's displacement law, which says that the product of lambda, this wavelength lambda, and the corresponding temperature at which this curve is obtained, so this is equal to constant. Okay, so now by applying this law to the given situation, so lambda star multiply by T star, that will be equal to lambda sun multiply by T sun. Okay, so basically we have to find the what is temperature of the star, and that is equal to lambda sun by lambda star multiply by T sun, and after substituting a value lambda sun, that is 5000 angstrom. Okay, and multiply by the corresponding temperature 10 power 4 Kelvin and divided by lambda star, which is 5 angstrom. Okay, so this gives T star equal to 10 power 7 Kelvin. So therefore D is the correct option here.